We were looking at measures of central tendency, which is how do you find the middle of your data. Those options, mean, median, and mode, really mean and median are the most helpful. When do we use the mean? If it's symmetric bell-shaped data, when do we go with the median? When it's skewed, when we have some extreme values. The next thing we want to look at is measures of dispersion. Okay, so the measures of center can be useful, but if I give a test and let's say it has an average of 80% and all of the scores were between 70 and 90. So everybody in the class got somewhere between a 70 and a 90. And then let's say another class took that test, they got an average of 80%. But in that class, all the scores were between 50 and 100. Is there a difference between those sets of data? Yeah, they both have the same middle, the 80%, but one of them, everybody scored pretty much the same, and the other, we had some pretty extreme values. We had some people that got a 50% on it. So we need to look at how spread out the data is. That's a measure of dispersion. How spread out are your values? And there's a few different things that we can look at there. So we're going to start with an example, which is part of the reason I printed this for you, because I have some larger sets of data and I figured you didn't want to try to copy all these down. So to order food at a McDonald's restaurant, one must choose from multiple lines. While at a Wendy's, one enters a single line. The following data is the wait time in minutes in line for a simple random sample of 30 customers at each restaurant during the lunch hour. For each of these, I want to give the mean wait time and look at the histograms. So how do we find the mean? Add them all up and divide by 30 in this case, yeah, however many there are. And we have two options. We can do this by hand, actually type them all in, add them up. We also talked yesterday about how if you put these into lists, it can find the mean for you. Do you guys have a preference? No? Okay, I'm going to show you another feature on your calculator. So let's do this. I want you to put all the McDonald's times in L1 and all the Wendy's times in L2. You have a couple different options for getting the mean. We did it yesterday. Do you guys remember what we went to? Set, calculate. And if you go to one variable statistics, you have to tell it which list do you want the stuff for. So you could do that for L1, and then you could go back in and do it for L2 and get both groups. We also have the option, you could go to stat, calculate two variable statistics. So the X list is L1, the Y list is L2. So it's going to use X's for the first list, Y for the second list. And if we calculate, it will give us a bunch of information for both lists. So X bar would be the mean of the first column, which L1 was my McDonald's. So my mean so I went stat, calculate two variable statistics. And then if I look down my list, it has a Y bar, which is the mean of the second group, so 1.39.
So it doesn't give you a median?
Oh no.
What's
Got
wrong?
him. Wait, no, maybe
Punch
not.
the
Maybe
number
not.
wrong.
This- Mine's 1.389 and yours is 1.3. Oh, okay.
Well, McDonald's was 1.389. The other one I have
Oh,
for Wendy's.
Yep. I'm right.
So if you look down, it has the Y bar. Now, you'll notice it does give you slightly different information than just the one variable statistics. Like, it gives a lot of things that we would not use. if you were wanting like your median and things like that, you would need to go through and do one variable statistics for each column. But this is just a fast way. If we have multiple sets, we can get it to get us both means at one time. Okay, did everybody figure out how to do that on their calculator? It's just another option. You could do them by hand. You could do the one variable statistics for both. So we got both means. So if I look at that, are they the same? No, but pretty close. Waiting 1.389 minutes is pretty much the same thing as waiting 1.39 minutes. So it looks like they are pretty much identical. The histograms, we could have our calculator do it. I actually went ahead, if you look on the next slide, I put them on there for you, just to kind of save some time. So if I look at these, what do you think? They had essentially the same mean for both groups. Are the histograms the same? Not really. McDonald's is very much skewed right. What does that mean in terms of your wait time? So if we look, you know, most people are going to get served within the first 30 seconds. But if you don't, there's probability you may be waiting up to 5 minutes. So most people are served immediately, but there's a skewed right, so we have more higher values. More people have to wait for their food. If we look at Wendy's, not very many people get served within the first 30 seconds, but most of them are served between 30 seconds and 2 minutes. Does anyone really have to wait too long? No. Here we don't have anybody waiting over 4 minutes, whereas McDonald's, we still had a few. So the mean told us that these were pretty much the same, but if I look at the histogram, they're really not. McDonald's, if you don't get served immediately, you're going to have to wait a while. Wendy's, it's pretty likely that you're going to get served in a short amount of time. All right. So the mean doesn't tell us everything that we might need to know from our data. So if we're looking at how spread out the values are, we can look at what's called the range. We just use capital R to stand for range, and it is the difference between the largest data value and the smallest data value. Do you guys have your formula packet that I gave you yesterday? So I told you, you're really not memorizing formulas now. Everything's going to be given to you. So if you look, yesterday we talked about population and sample mean, the third bullet, largest data value minus smallest data value. So it tells you how you find your range. And that gives us our spread. So let's go back to that example we did yesterday several times with our 7 employees. If I wanted the range, range is just your highest minus your lowest. So what was my highest commute time?
43.
Minus my lowest.
5.
So we have a range of 38 minutes. Now, range is kind of like the mean, in that it gives us a pretty good picture, but if I threw in a really high value, if I threw in that 130-minute commute time, what does that do to my range? Yeah, it makes it look huge, and in reality, everybody was pretty close with exception for that one person. So the range is like the mean. It's easily swayed if you have really high or low values. So if our data is skewed, it's not going to be as helpful. The other option we have is standard deviation. Okay, we start getting some nasty looking formulas here. Let's kind of talk about what this means. So standard deviation, that little Greek letter, it's called a sigma. If you forget what that letter stands for, if you look on your formula sheet, it has population standard deviation, and underneath it, sigma. So you can kind of remember what your variables stand for. So if we're looking at the whole population, there's a couple ways it can be calculated. Most of the time, I will probably just do this. So you have to take each individual observation, subtract the mean, and square it. Okay, so we know mu is the mean. This means the sum. So we're going to add all those up, divide by n. What do you think n represents? The number of observations we have, so we'll divide by n and take the square root of that. So this is not just a simple, quick calculation. It's going to take a little more time to get it. And like I said, there are options if you wanted to do it. They're all essentially the same. This formula is equivalent, but I think this one is probably the easiest if we are working things out. So let's take a look at it here. We have the travel times for our employees, and I want to find the population standard deviation. So when I have you do this, I would have you make a table, and I would put 3 columns on it. So I'm going to have one column for x, that's each value. Then we're going to do an x minus the mean, and x minus the mean squared. So my x's are my times, 23, 36, 23, 18, 5, 26, 40. All right, we did this one yesterday. Do you guys remember what we had for the mean on this yesterday? It's like our first example, maybe. Okay. So here's what we do. We come in, we do our value. So 23 minus the mean. So minus 24.86. I get negative 1.86. And then you square that. So next one, 36 minus 24.86 is 11.14. Square it. Do you guys see where I'm getting these values? 23, I already did that. We got negative 1.86. 3.4596. 18 minus 24.86. Square that. So, a quick check to kind of look for mistakes. X minus mu, each value minus the mean. What do you think that should add up to? If you have the middle, then you should have the same amount above and below, right? 0. So if we did it right, that should add up to 0. That's just a quick check to catch if any of your numbers are off. So this should always add to 0. Alright, let's add ours up and see if we have a mistake. Alright, did you get 0? I got negative 0.02. Is that what you guys got? Okay, so why didn't we get 0? I told you if we did it right, we should. Rounding error. What did we round? The mean yesterday was rounded. Remember, it had more decimal places. So it's because we have rounding error that it did not work out perfect, but it should still be very, very close to 0. So I'm feeling pretty confident about that. So then our formula for standard deviation, it looks really nasty, but what does this symbol mean? The sum. So we need to add up all of those values.
That's what I thought you were talking about.
Oh.
I'm really sorry. I can't help it. I have a song in my heart.
Do you guys get this 902.8572? Okay. Test or quiz, I strongly encourage you to show me your work. Don't just try to do the whole thing on the calculator, write out what your total was. So, standard deviation is the square root of this sum divided by n. What was my n? What's your mean? N is the number of values. 7. So we have the square root of that divided by 7, and I get a standard deviation of 11.3569. Okay, we will learn throughout the semester, we'll talk about standard deviation and what these numbers tell us, what is a good standard deviation versus a bad. But for right now, what you need to know is the higher the standard deviation, the more spread out your values are. Okay, so if we're looking at 2 sets and one has a standard deviation of 2 and one has a standard deviation of 11, the one with the 11 means your values are more spread out. All right. Do you guys want a faster way of doing this? It's kind of time consuming, isn't it? Okay, why don't you go to your calculator. All right, clear out the 2 lists that we have in our calculator. And in your L1, put these 7 values. Your 23, 36, 23, 18, 26, and 42. So we need to calculate one variable statistics for list 1. All right, what variable is standard deviation? Sigma. Look at your list of stuff. It's got an x bar, a sum of x squared, it has an s, and then it has a sigma. And 11 point, did you get the same thing?
Wait, what did you click after calc?
Stat, calculate, one variable statistic. So the same place we went to get the mean.
I thought I'd seen that.
Is it the circle with like the?
Uh-huh. And 11.3569, isn't that the same thing we got? Okay, go ahead and hit enter.
Oh my
So
god.
hit enter.
I'm never doing that again.
What?
Never dropping that.
All that work. Well, just say
And
come on, this correct.
Yes, so probably. Did you get it?
Yeah.
Okay. So most likely what you could expect, test or quiz for this chapter, I will probably ask you to do one of them by hand, probably be a small data set. And then after that point, we would just use our calculator because this is pretty time consuming. We're not usually dealing with a small set of nice numbers. So I may have you do one by hand with some nice pretty numbers just to make sure you understand the process, but then we will be using our calculator to find this. And even if I have to do one by hand, you can check it on your calculator now. Right? Okay. If you are dealing with a sample, the standard deviation calculation is just slightly different. And you notice on your calculator, it has an S sub x and it has a sigma sub x. The sigma is the population standard deviation. The S is the sample standard deviation. And you'll see those numbers are slightly different. So if your data is just a sample, when we calculate the standard deviation, we're going to use this formula. So S means sample standard deviation, which is on our formula sheet if we forget. What's X bar mean? The mean of the sample. So it's the same thing. You go through, you take each value minus the mean, add them all up, but this time you're dividing by n minus 1. So if my data, if I had been 7 employees from the school, okay, does the school have more than 7 employees?
Yeah.
Yes, so that would not have been everybody, so it would have been a sample. So I would have done the exact same process, but in my square root, I would have divided by 6 instead of 7. So it is important to know if you have a sample or a population when you calculate your standard deviation. It is slightly different. And we'll talk more about the why in the time to come. I did put just a very basic explanation on here. Later on in the semester, we'll talk about degrees of freedom. That's what the n minus 1 represents. And so basically, if you have a sample, you have 1 less degree of freedom. But we'll get more to that later. Right now, you just need to know how to use the formulas. All right, let's look at this one. Here are the results of a random sample taken from the travel time for my 7 employees. So, is this everybody? No, this was my sample. So if I wanted to do this standard deviation by hand, we need an x. Since I'm talking about a sample mean is x bar. Okay. I would need the mean of this group. Can you calculate that mean for me? Add those 3 numbers up. And divide by 3. So our mean is 22.333. So if I were going to do this by hand, x minus the mean, so 5 minus 22.333. Decimal places will make a big difference here. If I round to 3 versus 4 decimal places, my answers will be slightly different. So what trick did I tell you you could use to check your work? The x minus the x bar should add up to 0. If I add those, my calculator tells me 7e negative 4. That means 0.0007, so is that pretty close to 0? Yeah. So then we do need to add these up. So sample standard deviation is S. It's the sum of these divided by n minus 1. So what's my n here? 3. So we would just be dividing by 2. So I get a sample standard deviation of 15.8219. So how does that compare to my total group? It's close, but it's higher, which means my sample was more spread out than the original, which seems reasonable because I took the lowest value and one of the highest ones from my other data. So this is just a little more spread out.
I bet this would be really easy on Google Sheets.
Yeah, if you do formulas, it's not too bad at all. If you had done it on the calculator, then you would have been looking for that S, not sigma, because it said sample standard deviation. Alright, is this okay? Alright, so now I'm feeling really bad because I told you to delete all that data, and then the next example I had my McDonald's data again. So we're going to do it on my calculator up here because I haven't deleted those out. Okay? So if I wanted the standard deviation for Wendy's and McDonald's, we're just going to look at my calculator. Would I be looking at S or sigma? Is this a sample or a population? A sample. So we need the S. So McDonald's, my S was Wendy's. Scroll down a little bit. So Wendy's, my S was 0.7384. So what does that tell me? Yeah, McDonald's had a higher standard deviation, so their values are more spread out. This is a smaller standard deviation, so that means they are more consistent in the wait times. So if I'm going to pick one to go to, and I know it's about the same average for both, would you want the one that is always roughly about the same amount of wait time, or the one that could be fast or it could be really slow? You want McDonald's. Way to be different. I'm trying to make a point here. Come on. You would go with the more consistent one, okay? Because you have a better idea of how long you are going to wait there. Except for green. All right. Are we okay?
Yeah.
I'm almost ready to stop for today, I think. The next thing I have is variance. So variance is the square of the standard deviation. So I think, is this on your formula sheet? Yep, population variance is sigma squared, sample variance is S squared. So if you have your standard deviation, all you do is square it to get the variance. Variance is kind of like mode. It's there, it's something we can use. Sometimes we look at it, but it's not what we frequently go to. We usually just rely on that standard deviation. So, for example, okay, we already have this one in our calculator, right? That's the last one you guys put in your list. If I wanted the population and sample variance. So, my population standard deviation. We had that in our calculator, stat, calculate one variable statistics. Okay, my sigma was 11.3569. My sample standard deviation was 12.2669. Okay, so to get The variance, you just square it. So I get a variance of 128.979. My sample variance is 150.477. In terms of interpreting these, basically still the higher the number, the more spread out. Just take them to the second pattern. Everybody get those? Let's stop